You're like, this is nice.
All right. We'll use now the rest of the class just to cover as much of the practice midterm as we can. So starting with problem 1a, it says restate the following in statements in an if alpha then beta form. So alpha implies beta. All right. I will only mow the lawn if you pay me $20. What does that say? Is it saying if you pay me $20, I'll mow the lawn? Or if I mowed the lawn, then you paid me $20?
If the lawn is mowed, then you paid me $20.
If I mowed the lawn, then you paid me $20. So if, remember it's an if alpha then beta form. So you better have if, then one sentence, I mow the lawn, then you paid me $20. So better say if something, then something.
What's the... which way does the implication go on only if statements?
Only if alpha, only if beta is alpha implies beta. Alpha if beta is beta implies alpha.
So
I'll mow the lawn if you pay me $20 means that if you pay me $20, then I'll mow the lawn. I'll mow the lawn only if you pay me $20 means that if I mowed the lawn, you must have paid me $20.
I got that. That makes sense. Okay.
It's always helpful to think about in terms of fire and oxygen. There's fire only if there's oxygen. Means if there's fire, then there's oxygen. On the other hand, this one is going to be
Oxygen and fire.
there's oxygen if there's fire. Means that if there's fire, then there's oxygen. So think about it in terms of oxygen and fire, often useful for sanity checks. All right, everyone who passed the test got an A in the class. Does that mean if you got an A, you passed the test, or if you passed the test, you got an A?
If you pass the test, you got an A.
Everyone who passed the test got an A in the class. Sometimes another way to think about this is in terms of Venn diagrams. Everyone who passed the test, so here's everyone who passed, also got an A in the class. So that means if these are all the people who got an A in the class, we're guaranteed everyone who passed for sure got an A. But there could be people who got an A that did not pass the test. Okay. So write, if you pass the test, then you got an A. Write it as an if, alpha, then beta form. Make sure you have if, some sentence, then some sentence. All right, last one. Only the wise can understand this sentence. Only the wise can understand this sentence. What does that mean?
If you understand the statement, then you are wise.
Is it understand implies wise?
Yes.
Implies wise, or wise implies you understand?
Let's understand the positives.
Now, if you're getting stuck, only the wise can understand this statement. That means, out of everyone who understands, they come from people who are wise.
Yeah.
Only the wise can understand the statement means everyone who understands the statement must be wise.
Yeah.
So if you understand, then you're wise. It does not mean if you're wise, then you understand.
Yes.
Got the logic there? Sometimes a good one that I sometimes think in my head is only humans know algebra.
Yeah.
That means if you know algebra, you're human. It does not mean if you're human, you know algebra.
Right.
Okay, so that covers that one. Think that one's easy. You can easily do it. Next one. The only way for Dorothy to get to Oz is to follow the yellow brick road. What is that saying? Is that saying that if she follows the yellow brick road, she gets to Oz, or if she gets to Oz, then she follows the yellow brick road?
If she gets to Oz, she follows the road.
Right, that's saying getting to Oz implies following the yellow brick road, right? That's all it tells us. So the yellow brick road could go all over the place, but if you got to Oz, you for sure followed the yellow brick road.
Yeah.
Okay, so what can you conclude if Dorothy got to Oz? If she got to Oz, what can you conclude? She must have followed the yellow brick road. So for part A, she must have followed the yellow brick road. What do you conclude if Dorothy followed the yellow brick road?
Nothing conclusive.
Nothing.
Nothing new. If she followed the yellow brick road, then she followed the yellow brick road. Maybe she followed it for 3 steps and then stopped.
Right.
That doesn't mean she got to Oz. Maybe she died along the way. Poor girl got kidnapped. Who knows? Okay, think you're going that one. Problem 3. If P and Q are points in the interior of angle O, that's scary definition. You're for sure going to want to have that definition written down for your test.
Yep.
If P and Q are points in the interior of angle O, then so is a segment PQ. So, let's draw it. Here's O. We know P is in the interior. We know Q is in the interior, right?
Mm-hmm.
We're trying to prove that the whole segment P and Q is in the interior. Now, let's remind ourselves, what's the definition of a segment? What's the segment PQ?
It's PQ and all the points in between.
It's the point P, the point Q, and all the points between P and Q.
Yeah.
So I already know P and Q are in the interior. What remains to show is that any point between P and Q is in the interior.
Yes.
So let's pick a random point A between P and Q and show that it is also in the interior.
Yes.
We're going to do this by proof by contradiction. If A wasn't in the interior, where could it be?
On the
On
end.
the line or
It could be on the angle, so A could end up here. We'll call that A prime in our picture, just to help us think. And where else could it end up?
the exterior.
In the outside the angle somewhere. Could be somewhere right there. We'll call it A double prime.
Yeah.
So those are going to be 2 impossible pictures. Here's the problem with A prime being on the angle. I know that A would be between P and Q, right?
Yes.
So that would make my segment look like this. And how do I know that this can't be a segment?
There has to be some kind of double intersection.
No, it's not double intersection. It's something else. I'm trying to remember.
So let's handle this case as we
I
go.
remember. I know I did.
So, 1, let P, Q in the interior
There's an intersection, so P.
of angle O, comma, and let A such that P, A, Q. So I'm picking A to be some random point between P and Q. I need to prove that A is also in the interior.
If A's on the line, then doesn't that make P and Q on opposite sides?
Perfect. So, assume by way of contradiction that A is not in the interior. 3. So if A is not in the interior, where could it be? On the angle or in the exterior. Let's handle the on the angle case. If A is on angle O, comma, call it ray R. So we'll just let R be whatever side of angle O it's on, comma. Then PAQ tells me what?
The P and Q are on opposites.
That P and Q are on opposite sides of R. Right? What does it mean for 2 points to be on opposite sides of a line? There's a point on the line between them. So since A is on R and it's between P and Q, then P and Q are on opposite sides of R. How do I know that's impossible? Because they're both in the interior. And what does it mean to be in the interior? It means
Same side of
you're on this raised side of this line, and you're on this raised side of this line.
Yes.
So they have to be both on the same side of R. So that gives me P and Q on opposite sides of R. Contradiction. All right, 4. If A is in the exterior of O, and now let's think about that, of angle O. So what's the bad picture that gives us? So we handled that bad picture. Now let's handle this bad picture where A's down here. How do I know that this is an impossible picture?
Because it wouldn't intersect the rate wise.
Because then we're going to have segment PQ intersects this ray 2 times.
Okay.
Okay, so if it's in the exterior, comma, then A is on the opposite side of at least one of the rays. A could have been somewhere over here, and it could have been on the opposite side of both rays from the points, but it has to be on the opposite side of at least one of the rays.
Yep.
Then A is on the opposite side of one of the sides of O, we'll call it R, of angle O as P and Q, comma, call it R. So let R be whatever ray, the name of the ray that it's on the opposite side from. Okay. So now, since A is on the opposite side of the ray as P, what does that mean?
There's a point. in
On
here.
the line between.
There has to be a point on the line between them. So, what should we call that point?
B.
B.
B. I think when we did this before, just to try and trigger some memories, I think we called it R.
Did we?
Yeah.
Yes.
So, just trying to trigger some memories with some common labeling that we used.
Okay.
So I know there has to be R between P and A. Similarly, I know there has to be, we called it R prime between A and Q.
And so it intersects R twice.
Perfect.
Wait, how do we know that R and R prime aren't the same?
Because from PRA, well, I'll explain it as we go.
Okay.
So then there exists, remember our backward D? There exists R and R prime in little r, such that we have PRA and AR prime Q. Okay. Now, how do we know that R isn't secretly R prime? And it comes from our between us relations. Combining these two, we can combine this and this to get that we know R prime. A is between R and R prime. And anytime you have a between us relation, you're guaranteed that they are 3 distinct collinear points.
Okay. I see.
Good?
Yeah.
But anyways, so then there exists R and R prime, such that we have that and that, comma. And so, PQ intersects ray R twice, which we already know is impossible.
But theorem 3 1.
By theorem, whatever. So 6, therefore A is in the interior and we're done. I won't bother writing that. Any questions on that one? That's an old flashback, hope we are not regressing. Alright, problem 4. Prove that every line has a point on either side of it. Now, I remember last time when you guys did this problem, you constructed a line that had a point on either side of it. That is not what this says. This says prove every line has a point on either side of it. Those are 2 different things. So don't construct your line. Start out with a given line. So 1. Let L be a line. Now, given L, we need to prove it has a point on either side of it. So anyways, our picture so far, we just have an L like this. Now I'm trying to prove that there's a point on either side of it. So first off, how am I guaranteed that there's a point not on the line?
First postulate.
I think it's our first postulate for the whole class. There exists 3 non-collinear points in the plane. So I'm guaranteed by the first postulate that there exists some point P out here not on L. Okay, there we got 1. I'm also guaranteed that every line has 2 points, but for sure 1 point. So L for sure has a point called Q. And then using our line builder postulate, I'm guaranteed that there exists a point R such that PQR. And that's how I get a point on either side of the line. So let that be a line. 2 by 1, 1, comma, there exists P not on L, and by, I don't remember what it was, probably like 1, 3 or 1, 2, can't remember which one, comma, there exists Q on L. And then 3, our line builder postulate, I don't know if you remember what that was, probably 3 something, 3, 4 I think it was.
It's 2, 4.
Or 2, 4? Yeah. By 2, 4, comma, there exists R such that P, Q, R.
Basically,
Therefore, right. Therefore, P and R are on opposite sides of L. And we're done.
what's the difference between that and constructing a line? That's what you're talking about.
So when you construct a line, all you're proving is that there exists a line that has points on either side of it. You need to prove that every line has points on either side of it.
Did we?
If I say every human being has 2 hands, and you go grab Jack and say, look, here's Jack, he has 2 hands. You don't prove every human being has 2 hands, you prove Jack has 2 hands. So we need to start with a random line given to us. We know nothing about that line except for that's a line.
Right.
And we're going to prove, by virtue of it just being a line, it has points on either side of it.
How would you construct this otherwise?
How would you construct it otherwise? So here's the bad way to do it. So what a bunch of you did last time is, you said, by 1, 1, we're guaranteed that there's 3 non-collinear points. Now, construct a line through 2 of the points. And look at, we got a point on a side of a line. There's where some of you ended it. Others of you took the time to say, and we can use the line builder postulate to get a point over here, and so we got a point on either side of this line.
Is that valid?
No. All you did was find a line that has a point on either side. You need to show that every line has a point on either
You
side.
have to assume the line first.
So you need to be given the line and show any arbitrary line I give you, it has that property.
That makes sense.
Okay. Problem 5.
Yep.
In angle AOB, where AOB is not a straight angle, so it has an interior. Point P lies between A and B, prove it's in the interior. Okay. This was the easy one that you guys went nuts proving all sorts of convoluted ways.
Yeah.
Okay, so we're given angle AOB. So here's O, here's A, here's B, and we're given a point. What was the name of the point?
B.
P. We're told P is between A and B. We need to show it's in the interior of A and B. Okay. What does it mean for a point to be in the interior?
It means it's on the same side.
It's on the same side of this line as this ray, and it's on the same side of this line as this ray. Or in other words, we need to show that P is on B's side of A, and that P is on A side of B. So,
Oh, super.
yes. Let P such that APB in angle AOB. 2. Since APB, then P is on B's side of A. 3. Since APB, then P is on A's side of B. 4. Therefore, P is in the interior. Very simple proof. You don't need to go all sorts of let's assume it's not, oh no, we're getting double crossings somehow. Right?
If you did go about that route, how would you do it?
You're gonna make a mess. So if you try to do P is out here, well, if P is out here,
Could you say like PAB or something? And show
right, then you need to find the point on here between these two, but that's not trivial to do because your P could also be out here, and it could get kind of messy. Maybe your P is right here, and so maybe it intersects this way. And so you need to handle the case where it's on the opposite side of one ray, where it's on the opposite side of the other ray. So in either case, you're getting that there's a point on the rays between them. So
Okay.
we could have P, if P is not in the interior, well, we also need to handle the case where it's on the angle.
Okay.
And that one's pretty straightforward because then you have 2 points on the angle, and so this segment is intersecting the ray at 2 points. And then where it's outside, that means it has to be on the opposite side of at least one of the rays. Call it R, find the point on it, call it C. And now we are given that, well, we're given this exact picture. And so we're given that this segment intersects this ray at 2 points.
That doesn't seem too hard.
Now, it's just, it was almost given to you, and you instead went through all the work
Yeah.
as though,
So you don't need to construct lines through the rays to say it's on the side of one?
Well,
you could just reference it if you want. You could say, so it's on the opposite side of the line through R. But I'm okay with you talking about the side of the ray rather than the line. That's fairly common. Any other questions on 5? All right, 6. The easiest proof in the whole thing. Proof. If AB is not congruent to CD, okay. If AB is not congruent to CD, then AB is not equal to CD. 1. If AB equals CD, then AB is congruent to CD. How do I know that?
So I postulated 3
It's one of our postulate, the reflexive property, or whatever the number is. But we know that being congruent is reflexive. Every segment is congruent to itself. So if those segments are identical, they're congruent to each other. So now state the contrapositive. 2. Therefore, if alpha implies beta, not beta implies not alpha. Therefore, not beta implies not alpha. Sorry, I use a CD rather than saying therefore if this and this, but you get the same picture, right?
makes sense.
All there is to it. It's just the contrapositive of the reflexive property.
Alright.
Prove 0.9 repeating is equal to 1. Let x equal 0.9 repeating, right? Which gives me that, what does 10x equal to?
9.9.
9.9 repeating. 2. Then 10x minus x is equal to 10x minus x. Which gives me that 10x minus x is
9x.
9x. And 9 minus 0.99999, or 9.9999 minus all the 0.99999s leaves me 9, which gives me x is equal to 1.
Yep. That's your, yep.
It's okay in your proofs when you're doing algebra down the column like that to just go line, line, line. But you can explain all that with words if you want.
How do we know for sure that 9.9 repeating minus 9.9 repeating is 9? that trivial, or is there something behind that? How do we know we can just subtract a repeating decimal like that?
You could do a little bit of explanation. First off, anything minus itself is 0. And a sum can always be written out. 9 point its decimal can be expressed as 9 plus its decimal. That's what it means.
Right. Oh.
All right. Because shorthand, this is expressing an infinite sum if we were
Right.
going through the calculus of it.
And is it just trivial that you're able to subtract and add those infinite sums?
I wouldn't say it's completely trivial. We're obviously not going to do the calculus of dealing with infinite sums, but
But that's kind of just given to us. That it's going to be trivial.
yeah, we're not going to worry about it.
Did you also do that problem in terms of fractions? If you wanted to?
Yes. You would just have to express this as an infinite sum. That's 9/10 plus 9/100 plus 9,000 plus, that's what I meant by it's an infinite sum. It's an infinite sum of fractions. That's how we think about it.
Okay.
And so some infinite sum of fractions minus that exact infinite sum of fractions, since they're identical things, is 0.
0.
Yes.
Right.
Okay.
Okay.
Problem 8. A line L does not contain any of the vertices of triangle ABC. Alright, here's probably the hardest one on there. I don't know. That's a hard thing for me to say. I don't know what you guys find hard or easy. I'm always surprised. Okay, so we've got some triangle ABC. What side does L intersect?
AB.
AB.
No.
So we'll put AB here. And what side does it not intersect?
BC.
BC? Okay, so draw our line just so that makes sense. So our line comes like this, and we're trying to figure out what it does after that, right? So I know it doesn't contain any of the vertices. It goes through AB, and it doesn't go through BC. Prove that it goes through AC, right? So 1, let L and triangle ABC such that L intersects AB and L doesn't contain any of the vertices, or in other words, A is for sure not in L, B is for sure not in L, and C is for sure not in L. That's what we mean by it doesn't contain any of those vertices, doesn't go through those points.
Is there any notation or shorthand for intersects, or do you just have to
Yeah.
write
No.
it out every time?
You don't write set those notation for intersects?
Oh, if you're doing sets, sure.
You wouldn't do that for lines?
It's understood that when we're talking about two lines intersecting, we're talking about at a point.
So you wouldn't say,
This is perfectly valid notation. L intersects AB. Think about them as points. And then it's understood that the resulting set, that would really be a set containing a point, but we want to talk about the intersection as the point. So there's some imprecise language.
but that's valid shorthand.
It's unusual because here, this would make it think that you wanted to talk explicitly about the set containing that point rather than the point.
Which is a big
Because the intersection of two sets is explicitly a set.
That's a big difference.
It is a big difference. The set containing the point and the point itself are very different things. So it's imprecise language. It's a little bit vague language, but you can usually guess from context what would be more useful. If I did specifically want to talk about the set containing that point, I would for sure use set builder notation. That would help. Or set intersect notation. That would for sure keep it very clear to the reader what I'm talking about. Okay, anyways, so I got L like this. Okay, so L for sure intersects AB.
Yeah.
What does that mean?
There's a point in their intersection.
Yeah, we can say there's a point C here if we want. But that means that A and B must be on opposite sides of L using our, what's the postulate? The one that says that a line divides the plane.
One something.
Okay, so
It's 2, 5.
2, 5.
then A and B are on opposite sides of L, right? Now C is not on L. How do I know C is not on L?
Because it was.
Because
Because
it's
it's
intersecting.
it's verticing.
We assumed it.
Right. So C has to be on one of the sides of L.
Oh, you double labeled to do that way.
Yeah.
Oh, oops. We don't really care about that point. Okay, so C has to be on one of the sides of L.
Yes. Yes.
Can C be on the same side of L as, well, 3? Maybe I can just say it. Since BC does not intersect L, what do we know? If BC doesn't intersect L,
C and B must be on the same side.
then B and C have to be on the same side of L. That's what it means to be on the same side of L. The segment between you doesn't intersect it. What does it mean to be on opposite sides of L? The segment between you does intersect it. So, since BC does not intersect L, comma, then B and C are on the same side, or more importantly, what?
Opposite side of it.
Comma, and so A and C are on opposite sides. You see that? So we know A and C have to be on opposite sides of L. Because B and C are on the same side, and A and B are on opposite sides.
And C is not on L.
You and me are on the opposite sides of these desks. Alex and you are on the same side. Ergo, me and Alex are on opposite sides.
But what's the logic behind that?
The logic behind that is a line divides the plane into two sets.
Okay.
So you have to be in one set or the other. And we call those sets the sides of L.
Okay. I see it. I see it.
And so any 2 points not on L either have to be on the same side of L or on opposite sides.
That means there's a point in the intersection between A and C.
Perfect. 4. Then, since A and C are on opposite sides of L, what's the definition of being on opposite sides of a line?
There's a point on the line.
There's a point on the line between them. So then there must exist some point D between A and B, or A and C. Then there exists D on L such that A, D, C.
We're done.
And we're done. We were trying to prove that L intersects AC. I guess we could write one more line, therefore L intersects AC. Probably make it real clear.
When is it valid to use the there exists notations in the proofs? And when is it not?
I kind of hesitate with you guys using too much notation. I was going to write that, and then I backed out last second. There exists D in L such that that. That is when you would typically use it. Switching and putting an on is kind of weird. So I was being lazy,
Is it?
and I'm using it as shorthand.
Can we use the backwards E like wherever we want, or is there specific cases where we should?
Well, it's unusual to do what I had written there. Here is more usual. There exists D in L.
Mhm.
That is a more usual use case.
But we shouldn't be like mixing the words and then notation up.
But just randomly replacing exists with that symbol is in general bad. And if you do use it, always and forever, put what you're talking about exists instantly after it as with the name that you're going to apply to it.
Right.
You definitely don't do there exists a point D blah 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 blah. That just it turns it to a mess.
Horrendous, but-
So yeah, don't just go replacing the word there exists with backwards E. If you're not sure how to use the notation, it's always safer to not use it than to use it. I mean, the shorthand exists, and when I'm standing up here in front of you guys, I don't want to write a lot. Anyways, any questions on that proof? Okay, next one. prove the base angles of an isosceles triangle are congruent.
We already did.
Yep, we already did that one. Remind you how we did it since we weren't recording that. We take some triangle, A, and we're also going to call that A prime, B, and we're also going to call that C prime, and C, and we're also going to call that B prime. And we prove that triangle ABC is congruent to triangle A prime, B prime, C prime by side, angle, side. So I know that A prime, B prime is congruent to AB because it's an isosceles triangle. I know A is congruent to A prime because it's the same angle. And I know that AC is congruent to A prime, C prime because it's an isosceles triangle.
Right.
Those are the three pieces of logic there. Therefore, by side, angle, side, that triangle, this triangle, is congruent to this triangle.
Yep.
And so their corresponding angles, that and that, are congruent to each other.
Base angle.
So angle B is congruent to angle B prime.
Yep. Okay.
So there's a recap on the logic that you use for that proof. That will for sure be on your midterm. Okay, next one. Prove that any two right angles are congruent. How do we prove that any two right angles are congruent?
Looking at by way of contradiction, you're going to assume that one is bigger than the other one, and then you're going to show that can't be the case.
So I'll start out with, here's a right angle. I can't remember what we labeled these when we did it.
I have it right here.
Call this A, call this one A prime, or B, and then I think we use the primes for their complements.
So the supplements, yeah.
And let's draw it like this. We don't really need to worry too much about that. A prime, B, B prime. Okay. So, what are we going to assume? One, let angle A and angle B be right angles, comma, and let angle A prime and angle B prime be their adjacent supplements. Right? Setting out the picture so far. I'm trying to prove that A is congruent to B. We do it by way of contradiction. Assume by way of contradiction that angle A is not congruent, not congruent to angle B, comma, and call the larger angle A. So if they're not congruent, one has to be bigger than the other. We'll call A the bigger of the two, whichever that is.
And that's without loss of generality.
Without loss of generality, yes. Okay, so now I know that angle A is bigger than angle B. What does that mean?
It means there exists an angle.
So,
Array.
yeah, that means that we can come stick some ray. So that was A right there. We can come stick some ray in here, R, to map out angle, that's angle B, right? Same big as angle B. And that ray is going to be in the interior of angle A.
Yep.
Good? Also, what does it mean to be a right angle?
Means it's supplement.
Your supplement.
You're congruent to your supplement. So just remind ourselves of what I know from these pictures. Up here, I know that angle A is congruent to angle A prime. And I know down here that angle B is congruent to angle B prime.
Yep. Yep.
Okay. So now what am I going to get up here? up here, looking at that picture, I'm going to get that angle B is less than angle A, right?
Yes.
Angle A is going to be congruent to angle A prime, and angle A prime is going to be less than angle B prime, because B prime is going to be this now. So if that's B, here's B prime. I'm afraid of drawing it and making a mess of my picture. Here's B prime.
How do we know that for sure?
Because B prime, supplements are congruent to each other. So the supplement of B here is congruent to the supplement of B here.
And we know it has to be larger because B is smaller.
Because the angle it's using, notice that A's other ray is in the interior. Since this ray is in the interior of angle A, this is in the interior of that angle. That's how we're going to get this, but here's our contradiction.
Yeah.
Because angle B prime is congruent to angle B. So we're going to get angle B is less than angle B. Contradiction. There's the flow of the logic. So angle B is less than angle A is congruent to angle A prime is going to be less than angle B prime. We'll have to explain that piece in our proof, but then angle B prime is congruent to angle B. So I get angle B is less than angle B, contradiction.
Yeah.
So since angle B is less than angle A, 3, then there exists R, how do I want to say this so I don't make a mess? Then there exists R in the interior of angle A such that what's a clean way to say that? I want to talk such that that angle is congruent to angle B.
Why don't you just say Derek is the angle?
I want to name this, I'm going to call this ray R here, and this R prime, and I think that that will help us. So, let's we could probably use that. It's going to be up here. Let angle A and angle B be right angles, and let angle A prime and angle B prime be their adjacent supplements. So add right here. And let R be the shared side of angle A and angle A prime. With me?
Yeah.
So put that there. Okay. So 3. Then there exists R prime in the interior of angle A such that its angle is congruent to angle B, not using R prime. So, in other words, the other side we're going to use is the non-R prime side. So that tells us that we're talking about this angle. Okay. 4. Since R prime is in the interior of angle A prime, then it's in the exterior of, we didn't name that angle when we created it, did we? Then there exists r prime in the interior of angle A such that its angle,
Call it.
I'll just say the new angle here. So since r prime is in the interior of angle A, then it's in the exterior of the new angles. The new angles, comma, call it, what should we call it? C. So we'll call this up here C, but C is congruent to B, and we'll call this one C prime. That work for you?
Did you mean to write A prime on your step 4?
No.
Since r prime is in the interior of angle A, then it's in the exterior
Of that new angles.
Oh, I mixed up two things as I was going. Oh my goodness. Then it's in the exterior of angle A prime is all we were trying to say.
Oh yeah.
Then it's in the exterior of angle A prime. Okay.
Of.
All right, making all sorts of messes here. And now we don't have that angle label, do we?
No.
Then there exists r prime in the interior of angle A such that its angle is congruent to angle B, not using r prime, comma,
Call it angle C.
call it angle C. Okay, so now we have C named. Since r prime is in the interior of angle A, then it's in the exterior of angle A prime. And so, angle A prime is less than angle C prime, parentheses here, angle C's adjacent supplement. And again, probably should have labeled that up here. And let's angle C be its adjacent supplement. Bad labeling. But you good so far?
Yep.
Okay, and now we have everything ready to go. I probably have this proof written up better when we actually covered it in lecture. Taught more about how to label things ahead of time rather than making a mess. So then we get that angle A,
Angle B.
that angle B, which is congruent to angle C, is less than angle A. Angle A is congruent to angle A prime. Angle A prime is less than angle C prime, which is congruent to angle B prime. You follow all that logic? Angle B is congruent to C. C is less than A. So C prime is bigger than A prime because it has a side in A prime's exterior. And C prime, since it's the supplement of C, remember if two angles are congruent, their supplements are congruent. So that angle is congruent to that angle. So angle B is ultimately less than angle B prime.
Where's the conflict?
Because
But angle B is congruent to angle B prime. Contradiction. Therefore, A is congruent to B. Therefore, A is congruent to B. Proof by contradiction. Sorry about that one. Made a mess. All right, next. Prove the angles opposite the legs of a right triangle are acute angles. You know what the legs of a right triangle are? Not the hypotenuse. That's what the legs means. The sides that aren't the hypotenuse.
Did we define that?
I don't know.
They're
Yeah.
So- We've got some right angle, or right triangle. We'll set it up so that we'll do A, B, C, and we'll make C the right angle. What are we trying to prove? We're trying to prove that that angle and that angle are acute.
Less than.
Less than
Less
right.
than a right angle.
Less than right angles, so acute. So one, let triangle ABC be right such that, or maybe just say where angle C is the right angle. With me?
Yep.
Okay. 2, I'm just going to extend one of these and get a point out here, D. So let D such that DCB, just so we can name this angle now.
Yep.
3, observe that angle ACD is what? Is right. So now I know this is a right angle. So how do I know that this angle and this angle are less than that angle?
Because we know the exterior opposites are always greater.
Right. Here's an exterior angle. Its opposite interior angles have to be less than it.
Yes.
Since angle A and angle B are opposite interior angles, of angle ACD, comma, then they are just less than a right angle, or do we actually say acute? Acute, it says acute, which is less than a right angle. Same thing.
In 7.1 it says that it has to be less than the exterior opposite.
Yes.
Yes.
Then how would that work because they all add up to a straight angle, which would mean that A and B adds up to a right angle to add with the other right angle.
Yeah.
Right.
Your 45-degree angles.
It does.
They could be whatever. That could be 60, that could be 30, that could be 80, that could be 10.
Yes, which then becomes equal, not greater than the opposite
No, no,
exterior.
no.
Right.
Each
So this one by itself can never be 90 degrees because some has to go to that angle.
Yeah.
So this has to be less than 90 degrees.
Yes, but I'm saying it can equal it too, can't it?
No. So let's try and draw a triangle with 2 right angles.
No, I'm saying it doesn't. Does it have to be less than the combined? Does it have to be less than the opposite exterior?
No.
Okay.
It's just each angle.
No, just each angle by itself is less than the alternate
Yeah.
exterior angle. The sum could be more, the sum could be less. In that case, the sum was equal, but that was an accident.
Yeah, that's just because it's a right angle.
Right.
Right.
There's also,
Maybe
we're
it's
looking
always
at a
equal.
particular-
I'd have to, it's always going to be equal. In the case of Euclidean geometry, the sum of those two will always be that. Because that plus that has to be a straight angle, and that plus that has to be a straight angle.
Right.
So it will always be equal to the sum of the other two.
Okay. That makes sense.
Okay. Any other questions?
Makes total sense. I think we already did problem 12.
Problem 12, prove the following corollary. There is at most one line perpendicular to a given line from a point P.
We did that one.
Yeah, we already did that one. Let's just remind you of the logic of it rather than rewriting out the proof. So here's L. We could have P is here. So if P is there and we have 2 perpendicular lines to L, then what do we get?
That they have to be the same line.
We get this angle is the one and only angle on that side of L that's a right angle. And since this is also a right angle,
They have to be the
they
same.
have to be the same angle.
We know that by which postulate?
The postulate, it's going to be the first one for introducing angles, so probably 3-1, I'm guessing is what it is. It says given an,
No, that's just the existence populate for
Yeah,
segments.
the one we-
it's the one that says given a ray, then there's one and only one ray you can put on either side of that ray
5-1.
congruent to a given angle, so 5-1. Oh yeah, 3-1, that's clear back to between us,
Yeah, sweet mix.
I think.
Yeah, that 3-1 is just the existence of segments.
Segments, just segments.
Oh, that was segments. Okay. It's right, it's a corresponding one to 3-1. Okay, but with angles. So that is a case where P's right there, then you just got the same angle twice. Okay, now let's look at the other one. So if I have L here and P's here, and we get two perpendicular lines, how's that impossible? So if I get a line like that and a line like that, going through P, both perpendicular to L, this is a right angle and this is a right angle.
Because it creates an exterior opposite.
Right, so we've got a triangle then, and this is a exterior angle congruent to one of its opposite interiors, which is impossible. So that was the logic for that. Problem 13. In that isosceles triangle,
This is pretty much the same as what we did earlier.
very similar to what we already did, but
Just added extra
we'll just talk about the picture rather than drawing it all out. A, B, C. So we got A, B, C, D, E. We know what's congruent to what?
Angle ABD is congruent to angle CB.
ABD is congruent to
CB. We're trying to, and ABC is isosceles.
that is a bad way for me to phrase that. ABC is isosceles with AB congruent to BC is how I should have worded that. That is bad wording. You can't just assume you know which two sides are congruent.
Could you remind me?
So when we solve that, can we assume that A, B,
ABC.
and BC are?
Yes, likely if I gave you a problem like that on the test, I would give you credit no matter what because it's not your fault I wrote the problem bad.
And then we're trying to prove that angle BDE is congruent to angle BED.
So I'm trying to prove BDE. I'm trying to prove this angle is congruent to this angle.
This is the same problem as before.
Very similar to the problem that we had before.
I mean, kind of it is the same
Just
problem.
taking it.
It's almost the exact same problem. So that's what we're trying to prove. Here's what's given to us. Now since ABC is a isosceles triangle, the base angles are congruent. So I know this angle is congruent to this angle. So now I know that this triangle, ABD, is congruent to CBE in that order by angle side angle, which gives me that this side is congruent to this side.
Which gives you the base angle for the
And so now triangle BDE is isosceles, and so its base angles are congruent.
Yep.
Follow that?
Yes.
Okay, there's the logic for that one.
Solve that.
Next one, similar one. Let's see, something like this. A, B, C, D, angle 1, angle 3. Is 2 at the top?
No, 2 is at the
4 is at the
bottom.
top, 2's over here. Okay, and I know what is congruent to what?
No, angle 1 is congruent to angle 3.
So I know that this angle is congruent to this angle,
We know that AD is congruent to BC.
and I know that AD, this side, is congruent to
That's the bottom
BC.
side.
BC, that side.
We're trying to prove that angle 2 is congruent to angle 4.
Trying to prove angle 2 is congruent to angle 4.
My mind.
Okay,
Which you could find
So-
out.
notice that this side is congruent to itself.
Yeah.
So I know that by side, angle, side, notice that, let me write this one out just to make sure you're seeing it. Notice that triangle CBD, there, that triangle CBD, right here, boop, 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 is congruent to triangle, get the right order,
ADB.
ADB by side, angle, side. This side is the same as this side. That angle is the same as that angle. And this side is the same as this side. And so now I'm given that angle ABD. So ABD is CDB. Make sure you do the same order. That gives me that angle. If I pick over here, which one were we doing? Angle 4? CDB. If I use CDB, notice the ordering here. I did the first letter, the third letter, then the second is going to be congruent to the first letter, the third letter, then the second. ABD, which is angle 2. So that gives me that angle 4 is congruent to angle 2. But I want you to see how it comes exactly from saying these triangles are congruent. Sorry, missed my triangle sign.
Yeah. Makes sense.
So that triangle is congruent to that triangle, which means its angle using the first, third, second letter is congruent to its angle using the first, third, second letter. Order matters very much when we state these congruency relations. Problem 15. Determine if each of the following is true or false. If a theorem is true, its converse is true.
False.
False. What's the converse of alpha implies beta?
Not alpha implies not beta.
It's just beta implies alpha. That's the converse.
The contrapositive is
The contrapositive will be true. The converse not necessarily.
It's only true if it's a logical.
It's only true if they're logically equivalent. But yeah, you can never go from this to this. That's not a valid rule of logic. If you know algebra, then you're a human is very different from if you're a human, then you know algebra. They'll say very different things.
Yes, it is not.
Okay, the complement of a 40-degree angle is a 50-degree angle. So that one's correct. Notice that's complement, not supplement.
All right.
If segment AB intersects CD, so we got A, B, C, D. What angles are going to be congruent? The vertical angles and all straight angles are congruent to each other. So let's see what this one says. It says angle AOD. Oh, is where they intersect. Angle AOD is congruent to what? BOC. Is that what it said?
Yes.
BOC. So in that case, it stated something true.
So all that's true. No, A is not true.
So A was false, B was true, C was true. Prove the angle sum of any triangle is a straight angle is your last one.
Which we did.
Give you the idea of that one more time on camera. Plus we also have it recorded in lecture. But
Yeah. We've done the truth a lot.
yes, it's one that you hopefully will never forget. So trying to prove that the angle sum is a straight angle, how do we do it? We draw a line here parallel to this, and we extend those two lines. Put the A right here, I guess. Yeah. Okay, now this angle is congruent to that angle by corresponding angles. This angle is congruent to that angle by corresponding angles. And then these two are vertical angles. And so that angle plus that angle plus that angle is that angle plus that angle plus that angle is a straight angle.
Does it matter if you forget that?
Huh?
Does it matter if you forget that?
This should be one of the most basic things you know how to do from geometry. It's pretty bad not to know how to prove that the angle sum of a triangle is 180 degrees. You should be able to whip that out at any point. Just because it's very standard.
Okay.
It's like you should be able to whip out the Pythagorean theorem at any time.
Is that going to be useful? I don't know. Okay.
Okay, and that is it for your midterm review.
Is it-
Big midterm review. You can use calculators, you lucky guys.
It'll be so effective.
On top of that, you can take a sheet of notes. And you guys, if you're taking like pictures of the notes at the back of the book and printing that out, I don't care, that's fine.
Is it going to be an extra credit problem on midterm?
Most likely. I usually put one.
And it will be 16 problems.
It'll probably be 15 problems with an extra credit. It might be 10 problems with an extra credit. It's whatever I put on there.
One problem.
Oh, wow. Oh.
I know. That's what I'm here for. Anything else? Study, study, study.
Yes.
Please do good.
Yes.
And then make sure you bring all your homework to next class. And we'll just turn everything in and we'll be done. Those of you who do it